Hello everyone. So this is going to be a quick little discussion here, recitation for the rotational inertia lab. So the idea of this lab is that we want to measure the moment of inertia of different objects. So moment of inertia is roughly equivalent to the rotational equivalent of mass. Okay, so just like in normal linear motion, we have this quantity that's associated with a body that tells us kind of the proportionality between force applied and acceleration. In rotation, we have this quantity called moment of inertia, which would tell us the proportionality between a torque applied, which is our rotational equivalent of force, and the angular acceleration. And so the one of the differences here for a moment of inertia is that it does depend on the axis of rotation. And so what this means is that a single object can actually have multiple different moments of inertia depending on which axis it's rotating about. So let's say we have some kind of thin disk here, so something shaped somewhat like this. This disk will have a different moment of inertia if we're looking at some axis of rotation through the center of the disk, compared to if we are looking at some axis of rotation in this direction here, so in that kind of horizontal plane there, those will actually have different values for the moment of inertia. So whereas that object has a single value for a mass, it can have multiple different moments of inertia, which all depend on the axis of rotation. And this is because our kind of basic formula here to calculate the moment of inertia for some object is that we would sum up from I equal 1 to n mi times ri squared. So if we picture this disk as being made up of a bunch of kind of small little chunks of mass, and then we take the distance of that little chunk of mass, which is this m sub I here, and we take that distance from the axis of rotation, that's our ri there, so that's a little different than, say, a position r, so anything anywhere along this line will have the same capital R for that point, because it's the same distance from our axis of rotation. So we would then sum this up for all these little pieces of this disk to get its total moment of inertia. So this is kind of our basic definition. We could also, of course, express this. In this case, it would be more conveniently expressed as an integral, but you don't need to worry too much about that. Just suffice it to say that you can compute what you would expect this moment of inertia to be. And so if we do have some disk here, we expect the moment of inertia is going to be 1/2 the mass of the disk times the radius of the disk squared. And so we can compute a theoretical value for moments of inertia, but we want to actually calculate experimentally what they are. And so for that, we have to look at torques. So our rotational apparatus, which you will see at kind of the end of this video, there will be another little clip that's tacked on. Our rotational apparatus has a small spool where we can wind a string around it and apply some torque. And so if we have some top-down view of the spool, It would look something like this. And we have our axis of rotation, and we have a string that is wound around this. And it's going to come off at one side here. And so there's going to be some tension in our string. And that tension is going to then apply a torque to this spool. So if we call this, say, some little r there, then we know that our torque applied is going to be equal to the radius at which it's applied times the force that's applied, and then times the sine of the angle between them. But in this case, it's just going to be 90 degrees, and the sine of 90 degrees is just 1. So we are just left with the r times F applied, where this force that is applied here is our tension in the string. Okay, so we can control how much force is applied by putting different amounts of mass to hang off of the end of this string, and that can increase the force if we increase the mass, or we can decrease the force by decreasing the mass, and so on and so forth. But the thing is that we can then come up with some expression for this applied torque. And that's important because, like I was saying, our moment of inertia is kind of the rotational equivalent of our mass, and we can write a rotational equivalent for our Newton's second law. So if we sum all of the torques acting on some system, that should be equal to the moment of inertia of the system times our angular acceleration. So just to define all of these symbols here, that is torque. This is our moment of inertia. And this is our angular acceleration. Okay, so we can use this formula and our knowledge of forces and systems that are linearly accelerating, and we can end up actually deriving an expression here for what our moment of inertia of our system should be. So we can say that the sum of the torques on our system here, a rotating frame plus whatever object we've placed on it, is going to be our applied torque, which is going to be from this tension, and then we're going to have some frictional torque. So this is, we'll just say torque subscript lowercase f for the friction torque here. So this is friction. And that is, of course, going to be the moment of inertia of our system times our angular acceleration. Okay, so we can start using our force analyses here. So if we consider the mass hanger and the forces acting on the mass hanger, and if we call down our positive direction, because that's the direction things are going to move, so we might as well call that down. So we have, if we consider here's our mass hanger, you're going to have tension going that way. We're going to have the force of gravity, which is going to be m times g, pointing down, and we're going to call our down here our plus y direction. So we have our weight minus the tension, and that's going to be equal to the mass on the hanger times the acceleration of the hanger. And so this gives us then an expression for tension, right? So we can solve this part of our equation here for tension, and we can see this is going to be mg mg minus ma. So that gives us an expression for our tension, which we can then use to calculate what this applied torque is, right? So our applied torque is going to be the radius of the spool times this F applied, which is what we just computed up here, this tension, So this is going to be R times our tension, which is R times mg minus ma. And we know if we can kind of ignore the frictional torque, so if we can ignore friction, then we can say that the applied torque is then the only torque, and then that should be equal to our moment of inertia times the sorry, we don't need, so we can have R is equal to our R times mgma. So this is going to be our moment of inertia times our angular acceleration. But if you recall, we can say that the tangential acceleration is going to be equal to our alpha times r. And in other words, we can rewrite that as alpha is equal to the linear acceleration a over r. And so then we can plug in a over r here. And then from this expression, we just have to do some algebra to solve for this moment of inertia here. So you just have to multiply both sides by r over a, and we get that our moment of inertia is equal to the mass on the hanger times the radius of the spool squared times g over a minus 1. And so this is the equation that we're going to use in order to actually find the values of the moment of inertia of our different objects. So what we can do is just measure the a here, which is our linear acceleration of the mass hanger. And so we can measure this using our tracker software. So we just have to watch a video of the mass hanger falling as it's causing the rotating frame to spin. And we can track the position of that mass hanger. We can use the meter stick in the background of that to set our distance scale. And then we can get our, well, we're going to end up getting time and Vy data. So there's going to be a separate video that you can watch that actually goes through using Tracker to do this and shows what you need to do to help you out. But this is kind of our important equation for this experiment. So we're going to measure this acceleration, and that's going to give us a moment of inertia. Now, the thing that we need to remember is that this moment of inertia here, I, in this equation, is the moment of inertia of the system. And so, since this is of the system, our system is going to be equal to the rotating frame plus the object that we put on the rotating frame. So we have two components to our system. So the first thing you're going to do in this experiment is measure I for rotating frame. And then we can measure I for the frame plus disk or disk or ring. And then once we've got this information, we can get that our experimental values here, so our experimental I disk is equal to our I of the system minus the I of the frame. So we have to take the moment of inertia of the frame by itself, and we have to subtract that out from our measurement when we have the, say, the disk on the frame. So since the frame itself has mass and it is also rotating, its moment of inertia is going to contribute to our results. So we need to adjust this moment of inertia of our system by subtracting out the moment of inertia of the frame. And you have to do the same thing when we're considering the ring as well. Okay, so also given in the lab manual, there is a table there which gives us the kind of theoretical formulas for different objects. So we have an I disk equal 1/2 mr squared, and in the Canvas page for this, you should be given all this information here, the mass and the radius. And the other one that we're going to want, so we're calling this object a ring, but really what we want is, instead of using this ring here, we want to use an annular cylinder. So we are given that equation, and that's this 1/2 mr1 squared plus r2 squared. And so our ring, since it has some finite thickness to it, is not actually an ideal ring. So we have to use a slightly different form of our equation. And so you can calculate the moment of inertia this way. And then if you wanted, you could even compute what the theoretical value would be if you treated it as a ring, and see how far off you would have been based on the kind of thickness of that ring. So once you have your experimental values and your theoretical values from all the data that you are given, you can calculate the percent differences, and things should work out pretty well. I will tell you that for the disk here, I was able to get a percent difference of around 1%. And for the cylinder, I was able to get a percent difference of about 3%. And so that is using the exact same videos that you guys will be analyzing. So you should be able to get pretty good results out of this, as long as you are very careful when you're clicking and tracking the position of that mass hanger. So that is it for now. Hopefully everything here makes sense and you are clear on what you need to do. If you do have questions at any time, please don't hesitate to contact your TAs or contact me, and we will try to point you in the right direction. So this is the rotational inertia apparatus. It's a frame that spins. We can place different objects on top of it so that we can measure their moments of inertia. And in this experiment, the first thing that you do is you start by just taking this, we wind up our string here. Over on this side, we have a mass hanger with no additional weights on it, so it's just the 50 grams that is on the hanger itself. And we have this little frame here, so we can wind it up and let it go, and the frame will spin. What we are going to be doing is taking a video of this happening. So not this video, there will be a separate video that you will analyze, but the video will allow you to then track the acceleration of the frame, of the hanging mass. We can put our different objects onto the frame and repeat the same thing. So you kind of wind it up. We bring the hanger pretty close to the top there, and then we let it go. And you can see that it rotates much slower once we have some object on it. That's because we've increased the moment of inertia of the whole system. So now our moment of inertia of this is the moment of inertia of the frame plus the moment of inertia of the disk. So we have to take both of those into account. Okay? What this means for you when you are analyzing the data is that when you look at the acceleration for that hanging mass, which we will use to calculate the moment of inertia for these different objects, what you will be calculating there is actually the moment of inertia of the frame plus the object on the frame. And we will need to then calculate the moment of inertia of the frame separately so that we can subtract that out from the system moment of inertia to get the moment of inertia of the object itself. So that will be what you will ultimately end up doing. There will be another video in addition to this one that will explain things a bit more. Yep.